So now I am going to discuss the topic of error control. It's more general than error correction, and there are various techniques to make sure that the errors remain within certain bounds, and most of the time that is good enough for practical considerations. But to understand the subject in detail, we have to look at various elementary concepts essentially familiar from our daily life to figure out how to both characterize the error and then try to control it. So, one thing which is needed in any discussion of error control is digitization. You have to make the signal discrete in some sense to be able to identify the error and then try to correct for it. So, this is a necessity. Without it, you cannot correct errors at all. And we have enough experience if you just look at what all things are used in practical situation. All our languages have been digitized, consciously or unconsciously. Okay, whether it is a written language, whether it is a spoken language, whether it is music, and all the way even whether it is what is written in our genes. They have been discretized. And the reason, fundamental reason underlying that unless you do that, you cannot correct errors. And the important point is actually that quantum theory helps a little bit in the digitization, like the atoms are discrete, can't argue with that. Or even the energy levels get discrete once you go down to that level. So the nature helps in certain sense in terms of what are the physical properties of all the materials, and you can take advantage of that digitization in controlling the error. That doesn't mean that the analog information processing is useless. And you have to think about how does analog processing, which also we use many times, it means that you use continuous variables. What is the advantage behind it? And the little bit of analysis helps you figure out that moving things smoothly instead of in discrete steps, it helps in saving energy. And why it's connected to energy? Well, the underlying connection is between time and energy, they are in some sense conjugate variables in physics. So make time very precise and discrete, you lose something in energy. And you relax the constraint on a time little bit, well, you save something in energy. And we have enough examples of this also, both in our routine experience as well as the kind of devices which we make. And that is also convenient. And if you look at what life itself has done by evolution, has selected a particular combination which is phrased as a combination which in some sense is optimal for life. You don't want to spend too much energy, and yet you want to have a control over errors. So it combines both of them, and the phrase which is often used is digitally punctuated analog computation. Do something in the analog mode for some time, then you put a certain digitization control, then again evolve analog mode, etc. And this is how our brain works. Okay, it doesn't work completely digitally, and it doesn't work completely analog mode either. It's combination of both. And it has a definite advantage, and life has figured it out in whatever combinations these things are convenient, and it's again all over various natural processes. So this is something which we have to keep it at the back of the mind, and in error control, we'll kind of flip-flop between these two things, where digitization is needed and where analog stuff is convenient, and try to figure out the best of both the worlds. Okay. So the next thing is to now look at what are the sources of error. And various things can be included here. One of them is just environmental disturbance, is something external to the system, and it comes and spoils whatever you are working with. But that is not the only thing. Something which is necessary to do this information processing are the control signals, which is telling the system what to do. And these control signals themselves bring in certain amount of noise. So this is unavoidable, but you still have to learn how to control it. Okay. And the third thing, which is something which I have discussed already, and that the measurements are probabilistic. They are not necessarily going to get precise answer, you will get a distribution of answers. And from that you have to select what is the correct result. And this is something which I have already discussed, and I don't have anything more to add to it, but I can point out whatever is the best strategy, that is to transfer the whatever desired signal to ancilla bits or qubits, measure them, and then you have to actually use discrete measurement, same thing which I mentioned earlier. That the best strategy I have also again described, it comes from Chernoff bounds. And that is as much as we can do, or that is as much as we know how to do to be able to control these probabilistic measurements. And I am not going to say more about it. But the first 2 points I want to address. Okay. So now, yes, these disturbances are there. We need to quantify them. And quantification comes from estimating the rates of these processes. And for that, we essentially end up measuring the rates of these processes. Typically, they are some scattering phenomena. And the what you call the underlying physics which goes inside is kind of well known. And in quantum theory, it is known as Fermi's golden rule. Okay. So what does this rule say? It has essentially 3 parts. So the behavior is that the rate has some incident flux for the scattering process multiplied by the factor coming from what can be called interaction between components and the third factor is final state, well, let's call it density of state. How many states are available at the end of the process. And if you want to now make this smaller, you need to look at all these three factors and how are you going to reduce their magnitudes, and they all require different strategy, and they are all used in various different contexts. So how do you use the what you call design to cut down the incident flux? It's essentially the chances of various components coming together. So we have the strategy to reduce them in various ways. So here the obvious thing is to use shielding, thus cut down external disturbances coming in. Another feature is low temperature. It again reduces the incident factor which brings various components together. They are well protected. So essentially, these are all what you call features to control this environmental stuff. Shielding will control things like external electric magnetic fields. Temperature will control thermal disturbances, whatever it is, but you are trying to bring down that in various manner. How do you reduce interaction between components? Well, here you have to look at the natural properties of various systems. One good example is use photons. Photons directly don't interact with each other. They need a medium to be able to interact with it. So there will be unnecessary collisions which are prevented in a certain sense. And you don't have to go to very low temperature. You can work with photons at room temperature also without too much trouble. Another well-known system in this category is nuclear magnetic resonance. You use what are known as diamagnetic molecules, and the nuclear spins are essentially undisturbed by whatever is going on in the environment. And they live in their quantum state for a long time. You can think of, well, more sophisticated labels which will require some kind of tuning of various couplings. That becomes part of how to control these interactions. And one of the label which is important is something which is called a decoherence-free subspace, where the couplings are chosen to have some specific value, and that essentially cuts down the interaction with the environment. So that is a different kind of strategy, and they all have their own uses. What do you do to cut down the final number of possibilities? And again, you have to look at various physical features. One of them is a mass gap in the spectrum. What it does is, for the process to take place, there is a gap between the ground state and excited state, and you need that minimum energy for the process to complete. If that energy is not there, the process won't take place. And the best known example of this is superconductors. The electrons are there, but the resistance has dropped all the way to 0. It's not that the resistance is small, it is 0. And the reason is that the electrons are there, but there is a gap in the spectrum. They just don't have enough energy to go to the higher level, and they can have their own Coulomb force, doesn't matter. That does not produce any scattering at all. Of course, the exclusion principle is there as well, which helps that there are no available states for the electron to go, and the resistance just becomes 0. It's connected to the generic feature of this mass gap. Then, so these are superconductors. Another feature is inertia. And inertia means that it's not just one degree of freedom, but lots of degrees of freedom are essentially tied together, and if you want to disturb it, you have to move all of them together. And that gives a huge factor if the number of degrees of freedom which are tied together. And this feature is commonplace in what are known as coherent states. So the well-known example is lasers. You have lots of photons, all of them sitting in identical state, and that creates a situation where you want to disturb some feature of one photon. It doesn't work. You have to change the property of the whole lasers, and since there is a large number, there is an effect of just inertia, and the frequencies of lasers and whatever is coherent properties are very accurately specified, and you don't have to worry about it getting disturbed easily. Okay. So these are the features, and yes, we make use of them in whatever sense, but you have to understand some underlying physical properties which are involved, and provided you get some idea, we will put all those things in different manners. Okay. So, fine. One more thing I want to discuss. This can be called types of error. And this has two major categories, and they require different techniques to tackle them. And one of them is systematic, and the another one is statistical. So systematic errors are typically global and statistical errors are typically local. And we need to handle them. So systematic error just means that you have various parameters. You don't know whether the value assigned to them is the value you want or it is something else. And the first step then which is needed is a calibration. How do you know that the desired parameter has the correct value or not? And we used to have a old system where the calibration was done by some object kept in a museum, and you say that that has the correct value and that is used as a reference, and then everything else has to be compared that it has the right value or not. Not anymore. Okay. You want to define everything in terms of what is preserved or connected to quantities which do not change. And you have to figure out those particular quantities. So we have gone from reference systems to fundamental constants for the purpose of calibration. And here the best thing is to just give examples one by one. And so these are now called this SI criteria. SI stands for System International. Well, it's a French word, but fine. French version of it can be spelled out appropriately. So how do you now calibrate everything, all our fundamental properties, whether it is space or time or mass or electric field or charge or whatever it is you want to label. So I have to start one by one. The simplest things to quantify is time, or alternatively reciprocal of time, which is frequency. And how do you identify the behavior? Well, we say that the frequency already brings in a concept of an oscillator, and one cycle is equal to 2 pi, the fundamental constant. Pi is some value, and we just decided how you can decide a cycle. Well, cycle means that it starts somewhere and after some time gets back to its original value. And that is fine, but then you have to make sure that the system is such that the frequency doesn't change. But the frequency changes in different places, then it is no good. And here there is a one good property of the frequency, that even when you have a, say, a wave going through some material, the wavelength changes, but the frequency doesn't. Because the frequency cannot change, because whatever is going in, the same thing is coming out. And if it is coming out at a different frequency in between, there will be a pile up. That doesn't happen. And that is a nice property which says the medium can alter the wavelength, it can alter the speed of the wave, but it doesn't alter the frequency. On the other hand, there are other situations where frequency does change. If there is a damping, it does change the frequency, as you may have studied using just ordinary harmonic oscillator. And we have to make sure that the damping is very small. Or even more generally, there are well-known features like Doppler effect, which you may have encountered mostly in terms of a sound wave, but even for light, Doppler effect exists. It's a relativistic version of it, but it has to be avoided, and it is characterized by a relative velocity between the source and the observer. If you somehow keep that under control, then the Doppler shift can be avoided. That's not the end of the story. There are relativistic effects. Well-known thing is time dilation. So if there is time dilation, well, the whole thing is going to get spoiled. You can't afford to do that, so we will stick to non-relativistic speeds where these things can be done. But even then, that is not enough. You make it non-relativistic. There are effects coming from general relativity. The gravitational field itself, it produces a redshift. And redshift means that the time in a strong gravitational field does not move at the same rate as the low gravitational field. And there is nothing you can do about it. So you have to figure out, well, your gravitational redshift is under control or not. And this is not just hypothetical. This gravitational shifts and general relativity effects, our instruments have reached a precision where they are essential for keeping your system well behaved. If you don't include general relativity, your GPS will not work. Okay, it produces effects which will throw everything off in the measurement of time. And not only that, the scales are such that one can say that the head or the brain does not age at the same rate as my feet. There is a difference of gravitational field, and that gravitational redshift make the rate of time between the head and the feet different. And again, not hypothetical, our instruments have reached that sensitivity, so it can be measured. Okay. This means development in technology, but these things are there. And if they are there, you have to make sure that all these fluctuations are within our control. Okay. So here you have to worry about all kind of things which I went through. There is a damping, Dopplers, time dilation, gravitational redshift. All these things are there, but yes, people have worked through it, and the best standard is now is given in terms of the hyperfine transitions of this 133 isotope of cesium has been given certain number. It has this particular frequency, and that's it, it's exact. And the sign is then defined by how many those oscillations occur within whatever interval of time you want to measure. And yes, to make sure that all this stuff is there, you have to make sure that whatever that instrument is in a proper situation. And I think the current accuracy is 1 part in 10 raised to 15. That's how well you can maintain this particular standard. Yeah.
Transitions are usually defined by Poisson distribution.
Hmm?
Transitions.
Yeah.
Transitions are usually defined by Poisson distribution.
Yeah, but here you will look at the frequency of the photon which comes out. Okay, you are looking at individual photon frequency, or equivalently its energy, but whatever it is, it can be measured precisely. It has to be interpreted as a oscillatory wave, which you can mark. And the way it is done is there is a source and there is a detector. Both of them have to be there. The source is this particular atom, and the detector is another system which can absorb that particular light. And because of all the Doppler shift and all those things present, unless the detector has the correct property, it will not be able to absorb the light. And that is how the frequency is calibrated. Means there are all kind of things where I think people use also what are called fountains, where the atom is thrown up and it comes down after some time, and only if it comes back at the right time, it will be able to get into that particular field and emit or absorb the light. So these are various techniques, but it has become a what you call international standard. You can look up in many places what is a generic setup which is used. And it is not a complicated setup. It is something which can be made small enough and put in a satellite, because we need to put them in satellite to be able to handle GPS and all those kind of systems. So all those things have been designed and put in place. Okay. So once you have figured out how to calibrate time, the next thing to understand is length. And here relativity offers a great solution. That speed of light in vacuum is a constant, universal constant, and you just give it a value, so many meters per second. So once you have fixed the second, then multiply by this constant, and that will give you length. What about the third important object, which is mass? How do I calibrate that? And here there are a couple of choices. One of them is something called atomic mass unit, and it is just defined as one-twelfth the mass of the carbon-12 nucleus. And that carbon-12 nucleus is universal constant. No matter where you will go, you will find it to have same property and call it the standard of mass. That is at the atomic scale. At a larger scale, what is fixed is a Planck's constant. Or rather the reduced version of it, h cross, given some fixed value, and this is a fundamental thing in quantum mechanics because it is the unit for angular momentum. And we give it some value and don't change it. Okay, that is how this thing is done. It has a unit of either you call it angular momentum or equivalently energy multiplied by time. They are the same thing, and if you fix it, you have fixed the value of whatever the scale of mass there may be. Then you need one more, at least in our analysis, and that is electric charge. And this is well expressed by something which is treated as a dimensional parameter, the so-called fine structure constant of quantum electrodynamics, except for the fact that if you literally do quantum field theory, you will find out that it is scale dependent, that what you measure for the electron at rest is not the same as what you measure in some colliders, where also electric charge is part of the rate of interaction. So you have to fix the scale for it, and we go to the non-relativistic limit and say that I am going to measure whatever the value of this constant is where the electron is at rest, stationary. And if you do that, yes, you can assign it a value, and that will fix the standard for electric charge. And actually these days there is a good alternative for this, which comes from this quantum Hall effect. And it turns out to be a remarkable feature in the sense that the effect is very stable against impurities in the sample. So when you are measuring it at low temperature, the resistance shows sort of plateaus, and the plateaus are highly stable to, well, huge amount of accuracy and a little bit of impurity inside there, it doesn't matter. And the parameter which get fixed is so-called fundamental unit of resistance, which happens to be the ratio of E square over h, and we have fixed the Planck's constant, so it can give you the value of the electric charge. So this is something which we need to worry about when you are talking about calculating things at high precision. And many of the phenomena require those kind of high precision specifications. So every instrument which you deal with, it has to be nicely calibrated. And that is part of this systematic feature, that you have to fix the various scales. But then other kind of things appear where you have to go beyond calibration, and that is all connected with finding some, not a reference system, but the reference of the scale itself. What you call 0 may not be 0, it may be something else. Calibration will fix the proportionality constant of the scale, but it will not tell you where the 0 is. So how do you fix that? And it's best to give our common example from daily life to understand how this produces trouble. You go to buy something in a market, and the vendor will generally have a scale. And you put something on one side and something on the other side, and somehow you always end up losing. You don't understand how, but that scale is kind of imbalanced. Okay? So the vendor, of course, arranges things that the weight is always on the one side, and the item you buy is on the other side, and things are improperly loaded. The simplest answer is flip the two. Okay? Tell them to put the weight on this side and whatever you're buying on the other side, and then see whether he is happy with it or not. And it's a zero error. I mean, what you call equality is not the same thing, but what is that counter action is you have an inverse process available. So if you have an inverse process available, you can check whether what you did is properly in the direction, because after the inverse, it should come back. And if it doesn't come back to the original prop, well, you have to shuffle things around. The other things which is often used in measurement is you have a tape, but it has got worn out. That initial bit is kind of lost, so you can't measure it from 0. What you do is you measure it from another point, say 1, to some distance, and then do subtraction. So these are simple tricks, but you need the reference for 0. So they use all inverse operation or translation of the scale of this value actually. You can use this kind of things, and it is what I want to say, that it's generic. If you want to now use a more general operation, you want to really know whether there is a zero or not, you have to ask whether your inverse operation is available or not. You'll be able to use it in some sense, whether you can translate the whole thing by some unit and bring it back, if it is available or not, that you can use it. And the simple examples are, say you are putting a spin in a magnetic field. How do you know that the magnetic field is exactly zero or not? Means you are putting some magnetic field, but there may be some component from Earth's magnetic field or something else coming in, and it has shifted the values. Well, you have to take care of those corrections by figuring out whether I have an inverse operation available. I do one way and then the other way and see the difference and then cancel it out. And that is again a useful thing to keep in mind. Okay. So these are all means kind of generic features, and now I can be more specific about what we observe in dealing with quantum systems. And there are two parameters which are commonly quoted. So these are errors transform pure quantum to mixed states. Okay. And this is a generic behavior, some interaction with the environment has happened, and there is whatever correlation, entanglement between the two, and what you observe the system, it ends up being a mixed state, it's no longer a pure state. But to apply all this idea, you need to characterize this mixed state. What has changed and how much it has changed, both those things. And there is a well-known description for characterizing these mixed states. So there are two time scales which are used for description of this and they have, well, very simple names. One of them is called T1 and other is called T2. And what do they tell you? First of all, these are numbers which you can extract from experimental measurements without any theoretical modeling or any detailed analysis. And so now the theory has to be made which can explain whatever these rates denote. Okay. So T1 is a rate of change for diagonal elements, and T2 is a basically rate of change for of diagonal elements. Fairly straightforward things. But the density matrix we know have different properties for the diagonal and off diagonal elements. The diagonal elements actually give the probability of being in that particular component. So it's essentially connected with the population of the particular level. And what does this rate of change then mean? It says that how frequently the excited state will decay to the ground state. It measures essentially rates of that particular type. And those things happen. There is a decay rate for excited to ground state, and it's going to change the population of the diagonal elements, and T1 will characterize that decay. Okay. So this is a description of decay. What about the off diagonal elements? Well, it's a Hermitian matrix, and those elements are complex. So they not only have a magnitude, they have a phase. And the important point is that the phase also changes in this generic interaction with the environment, and the reason for it is directly connected to the scattering phenomena which I described. One of the common consequences of scattering is phase shift. And where does that phase shift go? It goes into the off diagonal elements. And so both this can be measured, T1 and T2. Of course, they are constraints that this density matrix, whatever it is positive semi-definite. Its eigenvalues cannot become negatives, and it implies that this, what is T2 is it's less than or equal to 2T1. It's yeah. That is bounded, the off diagonal elements decay at certain rate. The diagonal one also decay at a certain rate, and the relation is well, you can just take a 2 by 2 matrix and calculate the determinant and ask it to be positive, and you will get this particular relation. That is kind of mathematical part, but in practice what you find is this T2 is much smaller than T1, and this is a phenomenon which is known as decoherence. The off diagonal elements of the density matrix are also called coherences in different languages, and what you find is they decay. and they decay very fast. Or let me, the, no, these are time scale. Time scale is opposite the rate of the decay. I think I messed up all the inequalities. So T2 is extremely, yeah, it is short. So yeah, rate of decay is 1 over the time scale. Okay, the rate of decay is very fast. So this is what is observed, and well, it tells you that you have to be very careful in protecting against the scattering and worrying about the decays up to some extent. And here there is a what you call an observation which comes from wave dynamics, and it's useful to keep in mind. That in the quantum language, I can write the statement that superposition is generally much more stable, I should say. Than entanglement. That is this phenomena of decoherence. Entanglement will describe the off-diagonal correlations between the system and the environment. Superposition is just a components of the diagonal system, and this is something which is observed all the time. And it also tells you that when you are trying to look at various results, which are the ones which require much more care than some other ones which are fairly stable. Okay. Okay. Fine. So this is all kind of background on various things, but you have to know this well, generic description, classification, whatever you want to call it, to understand everything that we need to deal with. And now I can be much more specific about what we do in terms of a strategy to conquer all these varieties of things which go on. Okay. So no matter which scheme you work with, to be able to get rid of the errors, you have to pay a price, and the price is always some redundancy. It may be as simple a thing as a majority rule, but some extra burden will come. There is a cost to be able to do that. And of course, we try to minimize whatever that cost is in whatever scheme that is implemented, but you cannot do without it. And where does this cost go? That you use it to separate the scale of the signal from that of the error. If the signal is local, well, try to have a situation where the error is global. And if the error is local, well, make the signal global. Both ways are possible, but you need to separate it, and after separating it, that is making use of the redundancy, you might need extra space to separate these two. You can wipe out one of them and preserve the other one. That is the generic situation. And the common model which is used is the error is local and you spread out the signal on a larger scale. That is something like this majority rule. The individual component may get disturbed, but the majority doesn't. But the other way around is also possible, and that is another feature which I will mention a little bit later. And then what are called local, there's the first part. You make the signal global, and then you can do discretization to put a boundary between the two. Sometimes you use topology also to extract the global feature without worrying about local disturbances, and that allows you to go on with a protected signal in presence of certain type of noise. But the converse also I can point out. Global errors. Is that in two parts. Is a converse that if you know that the error is global, you can find a smaller subspace in which there is no error. And the generic label for this is decoherence free. The error may be not decoherence type, but that is the label which is used. So let me give a example, and this needs knowledge of type of error, because that will decide how you are going to choose the subspace. Okay. So the very simple example of this particular type is a biased coin. You know that the unbiased coin should give you head and tail with equal probability. But what you have is some coin. And in some sense, basically, you don't know where the zero is. It will give head with one probability and tail with 1 minus that probability. How do you get rid of that error? It's going to occur every time you toss the coin. So then you look for a subspace of these multiple trials where this error disappears. Okay. So if you have bias coin, you toss it twice, which means there are 4 possibilities. And then you do a mapping that if it is first time h and second time t, call it 0, first time t, second time h, call it 1. And even if the probabilities are not equal, these two have the same probabilities. And the other stuff you throw away. There will be trial. So that is the price you are paying. There is a redundancy. Not going to work all the time. And that extra part is what is outside the subspace. You are choosing a subspace of the result to get rid of the error, and it can be done without worrying about how much bias is there. It works. But you assume something that the coin, you do multiple operations, but they are of this IID, identical individual distribution type. Okay, something you have to keep in mind to be able to do that. And this has a generalization in this scattering language as well. And I can say that there is a qubit 0 state which scatters with one rate and one state which scatters with another rate. It happens. You don't have any control over it. So, well, I will take just a reference without too much trouble. This happens. I don't know what that phase is. So, what do you do? Again, you keep a system which has 2 qubits. And you look at only the states which are either 0, 1 and 1, 0. And ignore. The other two. So yeah, scattering will happen, but both of these things will be shifted by the same phase. And the global phase can be factored out of the quantum theory, not much of a consequence, and you have to throw out the other phase. So yes, there is a redundancy. You are discarding something, but you are choosing a subspace in which this noise has no effect. And these are the stepping stones in some sense to construct this kind of decoherence free subspace. That yes, the noise is there, but you can choose your variables cleverly so that the subspace is protected against the noise. And to be able to do that, you have to know the type of noise. Can't do it without. But this is a useful technique, and it's something which can be implemented without too much trouble. Okay. What else? Well, there is something which has been pointed out as a contrast to the classical error correction systems, and I can emphasize it as well. And that is, all these tricks are possible, even though the quantum stuff is more complicated. And that there are more type of errors compared to the classical situations. For qubit, there are disturbances which can be labeled by the 3 different polymatrices. And the classical one is only something which is called a bit flip, but here there is something which can be called as a phase flip, or both of them together. So yes, there are more types of errors to protect a qubit against, but you can counter that. The second thing is the general description of Hilbert space is as a continuous space, and it's not digitized automatically like the binary system. But yes, you can still get around with errors by discretizing these continuous variables in some sense, and the process which helps in the discretization is measurement itself. That even though the state in the Hilbert space may be some continuous value, when you measure it, you are going to get discrete answers. And you make use of it to get around the continuous variables. Yeah.
Can we not say that before measurement, the state would still be superposition of discrete states, not continuous? How it can be possible that it would be before it was continuous, after measurement only discrete?
The dynamics of the evolution is continuous. And as I said at the very beginning of this lecture, without discretization, error correction is impossible. So where is the discretization going to come from? The discretization comes through measurement. Otherwise, it is just going around in some Hilbert space. You don't know whether it's a genuine signal or it fluctuated because of the error. You cannot separate. And so, yes, to implement error correction, you must perform measurement, but you do a clever trick that before you perform a measurement, you separate the signal and error. So the part which you consider as an error, that is a part which you have to diagnose by measurement and then take the necessary action. So it's a jugglery, but yes, you have to do that, and only then you will succeed in error correction. The third thing is, well, together with measurement, comes another caveat that it's a projective process. So when you measure it, something is lost. The signal was originally Hilbert space. Now you get only one eigenvector, all the other eigenvectors are gone. And there is no way to get it back. So you have to get around that, and that is another thing, that the only error is you have to be careful in what you measure. You measure the error where something is lost, doesn't matter, and leave the signal unchanged. And that is buried inside here with all the separation of scales. You have to do that, otherwise you will lose the signal, and you don't want to do that. And what these two things together do is, initially the error may be small in the fluctuation, but when you do a projective measurement, it will either take you to the zero error type or a maximum error type. And that signal of the projection then can allow you, if zero error, don't do anything. If it is projected to the one error, then make a large transformation and go back. You have to do that, otherwise the scheme will break down, but it's possible. And yet another thing is no cloning, where the classical idea like majority rules don't work. Can't have multiple copies of the same system. And you have to get around that was as well. So what you do is use something which is available, which is entanglement, and don't try to use multiple copies. They are not available in foolproof form in quantum theory. And okay, so what does mean is if I have many copies, say alpha 0 plus beta 1 raised to some single qubit with 3 copies will look like that. You don't want to use that, that is not allowed. But what is allowed is This is how it works. It's not copies, but it's untangled state. And you can do that, and people figured out that all these things are possible. Actually, it was Peter Shor who wrote it down very cleanly that yes, you can overcome all these obstacles in a quantum theory, and once you have done that, you have a correction procedure. And what is built on those things is something which is much more ambitious than whatever I have been talking about. It goes by the name of fault-tolerant computation. I'm not going to discuss this in this particular course, but I will only give the definition. There is a separate course exclusively on this particular topic going on in the electrical communications department, and there the various strategies are discussed, but the result is that it needs complete encoding of the algorithm, which means from the input to the output. Nowhere you get out of the coded system that makes a whole dynamics and operations of the algorithm look complicated, but that is what fault-tolerant computation aims to do. Then the result is protected forever. Forever means as long as you want to run the computer. Provided the error rate is below non-zero threshold. Important point is the threshold is non-zero, and this is the characterization of the complexity class, which was called bounded error quantum polynomial computation. The bounded error means this threshold has some non-zero value. What that value is important in practical considerations, and the purpose of designs of all this fault-tolerant scheme is to make this threshold as large as possible. None of the present quantum devices are anywhere close to this particular situation. It will require some technological breakthrough or many years to get there, but theoretically it has been proven that yes, this is possible, and the advantage of this particular strategy is that you do not need to characterize what is the type of noise which is present in the system, because it will get rid of all types of noises. So, of course, it is a tougher job, and what I am going to stick to in the lectures that follow is not such an ambitious goal, but where I know something about the type of noise which exists. And with that particular knowledge, try to control it as well as possible, and those techniques go under the name not error correction, but error mitigation. The noise is not completely discarded, but it just kept under control. So, that is stuff which will follow in the coming lectures. Only? Yeah, so what you have is a larger space with redundancy. Okay? There is signal and error, both are present inside. So now you design your protocol such that the signal is in one subspace and the error is in the other subspace. All the cleverness of the algorithm or the code goes into designing that thing, but it can be done. And so once that is done, you will measure the error subspace to find out what is the error and correct for it without disturbing what is there in the signal subspace, because that has to be protected. And that is that is essentially the code. How do you do that? No, you can do it in this fault tolerant scheme without knowing anything about the encoded state. You can still separate them, because what it means is this kind of a situation, that you have to make the signal global and the error local in some particular manner. I am just using more general term that they are at two different scales, and it assumes that the error is of particular type. Typically, the errors are assumed to be local, that it can occur at individual locations, but independently at each individual location. The signal is non-local, which is encoded into correlated states of this particular type. It's spread out. And then if you have a disturbance on one of them, well, you can use the other ones and do some kind of a majority rule analysis to recover the state. But that is the procedure. There is nothing what you call obstruction in terms of principle, but you have to work to figure out the appropriate code.